Good morning and welcome to RMS618 Advanced Statistics. We're actually going to be talking about Module 1 today. These modules will cover correlation and simple linear regression, multiple regression, logistic regression, MANOVA and MANCOVA, and finally, number 5 will cover factor analysis. This Module 1, correlation and simple linear regression, we remember what bivariate correlation is. We're measuring the degree of relationship between two variables. We know this relationship is linear. In basic statistics, we covered correlation strength. This is pretty self-explanatory. Positive correlations and negative correlations, and so on and so forth. Scatter plots, the visual representations for correlations. Here we see a perfect positive correlation. Here a perfect negative correlation. Here we see no correlation. Here we see a curvilinear relationship, which we know is no correlation. Also, we remember as correlations increase in strength, the data points become more and more constricted. As correlations decrease in strength, the data points become more and more less bunched. So here we see the situation of total randomness, a correlation of 0. Pearson correlations are used, if we remember, at the ratio level and the interval level, also called continuous data. Spearman correlations are used with ranked data at the ordinal level. Discussion number 1, we see scatter plots correlating systolic volume with different dependent variables. Let's answer these true-false questions. There is a fair correlation between wedge pressure and systolic volume in the septic shock graph. A fair correlation. I would say this is a fair correlation. That is true. Here, there is no correlation between wedge pressure and systolic volume in the cardiogenic shock graph. That's actually false. That's false. A Spearman correlation coefficient is recommended for this data set. That is also false. Okay, we know that Spearman correlations are used with data at the ordinal level. Which correlational coefficient would you use to examine the relationship between ranking of the country's infant mortality rate and GNP ranking? We know it's obviously B, the Spearman correlation, okay? Spearman's rho. Which test would you use to examine whether there is a statistically significant difference between the mean blood pressure with respect to high-low sodium diet? Okay, we know that the two independent sample t-test would be the appropriate analysis. Okay, A, B, and D would be false. Now we have an SPSS sample problem. A researcher's examining factors that influence reading scores among children. Using SPSS, compute the Pearson's correlation coefficient and p-value for age in years and reading ability. Two variables, age and reading ability. We see our data set. This is a typical SPSS data set. We see our variables. And we bring the two variables into the variable box. We're going to run a Pearson correlation. We're going to run a two-tailed test, which we know predicts that the correlation will either be positive or negative. And it's going to flag the significant correlations. Here we have our SPSS output. We see a correlation, positive correlation of 0.782, with 108 research subjects. We see a p-value of 0.000, which we know is significant at alpha 0.05. So therefore, the two variables are strongly correlated. Now you notice this notation. This is the correct notation. All right, R brackets. This is degrees of freedom. We have our Pearson R, comma, p is less than alpha. This is how we report correlations in the scientific literature when we're writing research reports and so on and so forth. Discussion number 4, a Spearman correlation coefficient was computed in SPSS and the following results were obtained. Here we have a very, very weak correlation, and we see a p-value of 0.308, which is greater than 0.05. Okay, so we have a non-significant correlation. Let's answer these questions. What is the strength of the correlation coefficient? I would say, of course, weak or none. True or false? The p-value is statistically significant. It's obviously false. Okay, p is greater than alpha. This number is greater than an alpha of 0.05. So we, in this case, would accept the null. We have a non-significant correlation. Partial correlation deals with factoring out the effect of some other confounding variable or some third variable. We get a little bit clearer picture as to what's going on in terms of the relationship between x and y. Measures the degree of relationship between two variables while controlling for a third or more variables. Another sample problem. A researcher would like to determine the correlation between age and reading ability while controlling for the effect of gender. So they're going to factor out the effects of gender on the relationship. Gives a clearer picture as to what's going on. So again, we bring the variables over, and we're going to control for gender. We're going to run a two-tailed test, and it's going to display the significance level. And here we have our output. It appears that reading ability and age are very strongly correlated. And we have statistical significance at alpha 0.05, so p is less than 0.05. Let's answer the questions. How would you interpret the strength of the correlation between age and reading ability? I would characterize this as rather strong. Okay, pretty strong positive relationship. Is the p-value statistically significant? Yes. Why is that? Well, if p is less than alpha, reject the null. P is obviously less than an alpha of 0.05, or in this case 0.1. We would reject the null. We have a statistically significant correlation between age and reading ability, factoring out the effects of gender. Now we proceed into linear regression. Predicting y from x using this simple linear regression equation. So we're modeling the relationship between two variables by fitting a linear equation to the observed data. Now we have some assumptions that go along with this. We have linearity, okay, so we assume that the dependent variable is indeed linearly related to the independent variable. The deviations from the regression line, that's called residuals, follow a normal distribution. Here we have a data set, x and y, and a scatter plot. And it's obvious, we have a positive correlations, data point is going up and to the right, down and to the left. And actually R² is 0.964. R is around 0.98. Okay, so we indeed have linearity in this particular case. The linear regression equation, y equals a plus bx. Now this symbol is actually alpha, which is incorrect. Okay. And beta is actually the standardized regression coefficient, so b is actually the slope. Regardless, we have an equation. Y, it actually should be y prime equals 0.081. That is the y-intercept, plus 0.283x. So we see, this is the point where it crosses the y-intercept. And rise over run is 0.283. Okay, so we see change in y, change in x, and so on and so forth. Residuals, deviations from the fitted line to the observed values to investigate the assumption of linearity. Okay, so we see we have a linear relationship. It's pretty obvious. And There are many forms of regression. There are many ways to compute regression. We're going to use the least squares method. It's actually the most common for fitting the regression line. We will calculate the intercept and the slope for the best fitting line by minimizing the sum of squares of the residuals. It actually minimizes the distance from every bivariate data point, from the line. And from basic statistics, we remember R squared, that amount of shared variation between x and y, or the proportion of variability that can be explained by the regression equation. Okay. Calculating this, sum of squares of distance of points from best fit curve. Okay, the range of R squared we know is from 0 to 1, because when we square R, we always get a positive value. So, higher R squares imply higher explanatory power. Discussion number 5. Now, you see we have a scatter plot here. A researcher obtained the following regression line for the data set. What regression equation can be used to model the relationship between the variables? We have 4 choices here. Let's take a look at this. The y-intercept crosses the y-axis at a value a little bit more than 1. So the correct answer is either this or this. Rise over run, rise over run. I would say that the correct answer is C. I would say that the correct answer is this equation. Okay. SPSS, doing linear regression in SPSS. Okay, we bring the variables over. Dependent variable reading ability, independent variable age in years. Here is our output. We have an overall R of 0.782, R squared 0.612, adjusted R squared 0.608. What do these results indicate? All right, we would say 61% of the variance in Y can be explained by X. We get that from this or this figure right here. And the model does fit the data well. This is incorrect, okay? This is also incorrect. The results look to be statistically significant. And we see that is the case when we look at the ANOVA table, all right? P is 0.000, which is less than 0.05. So we have a significant model here. So the results are indeed statistically significant. So it would be true. Unstandardized and standardized coefficients. Okay. The unstandardized coefficient is in the same scale, which in this case years. Standardized coefficient, scale between 0 and 1. So this has actually been transformed to this. All right. What do these results indicate? The predictor is statistically significant. Okay. The regression equation is 0.474. 19.59. That's the y-intercept plus 4.74x. This is just reversed a little bit. Both A and B are correct. Reporting results. Check the assumptions. The linear assumption was a check by simple scatter plot. The graph shows the linearity between the two variables. The results of simple regression shows that 60.8% of the variance can be explained by the linear regression model. Okay, and we see proper notation here. 1 and 106 degrees of freedom. Here is our F statistic, comma, P is less than alpha. Okay, P is less than 0.01. To summarize, we talked about the bivariate correlations, strength and direction, scatter plots, the visual representation, Pearson R versus Spearman's rho. Okay, we know this is used with continuous data, interval ratio. Spearman is used with rank data. Partial correlations, where we factor out the effects of some confounding variable on the relationship, gives us a little clearer picture as to what's going on. And then the simple linear regression piece, whereby we predict y from x using this simple linear regression equation and fitting the model exercise. Researchers examining factors influencing quadriceps strength. Use SPSS on this data set to answer the following questions. What is the correlation between age and quadriceps strength? Is it statistically significant? What is the correlation between age and quadriceps strength after controlling for height? Is it statistically significant? Here we have it wants us to perform linear regression to examine the effect of age on quadriceps strength. How much of the variance in quadriceps strength can be explained by age? We know that's R squared. Is the model statistically significant? What is the regression equation? Here we have our correlation between age and quadriceps strength. We see a moderate negative correlation. It is significant at alpha 0.05, p is 0.007 with 41 research subjects. So this is saying as age increases, quadriceps strength decreases. This may be a biased sample. Fair correlation. Correlation between age and quadriceps strength controlling for height. Okay, so we factor out the effects of height on these variables. All right, we continue to see a negative correlation, not quite as strong, negative 0.322. P is actually 0.043, which is less than alpha. We have a statistically significant partial correlation between age and quadriceps strength, controlling for height. Model summary. Okay, this model is not that predictive. All right, about 15.3% of the variation in y can be explained by the variation in x. So, you know, although we have a significant model in terms of the ability to predict, the model is not that predictive. It's not that predictive. And again, we see the notation. Okay, F at 1 and 39 degrees of freedom and reporting the p-value. Coefficients. Coefficients. Okay, we have the y-intercept, we have b, and we have beta. And of course, you know, statistically significant results at alpha 0.05. Here is our equation. You see they're using b. And you know, in terms of coefficient, and then reporting y-intercept that way. Questions? If there are any questions, please address those questions on the discussion board. And this concludes the presentation for Module 1, Correlation and Simple Linear Regression. Have a good day.